Thanks for joining us at Tea Leaves Programming. Today we're programming like it's 1979. Today, Haskell for Dilettantes. We're kicking off our series that is going to cover the Haskell programming language and try to give you my opinion about what makes it special, what makes it really cool, and also try and give you, if possible, a different view, a different perspective into one way to learn the language. Now, these videos are going to go up about once a week. However, I am making them at a more frequent clip. If you can't wait to see them, you can become a member of Tea Leaves Programming at the early access or higher level. And you'll get access to them basically as soon as I record them. Very often the early access issues have bugs, so if you do become a member, I would appreciate any feedback you give. So today I'm just going to be setting the table. I know there's a lot of introduction in this type of class, but you need to understand what I'm doing and how I'm going to be doing it. So first of all, if you don't have a Haskell programming environment, the simplest thing to do is to go to haskell.org and click Get Started. It will give you installation instructions. If you're on Windows, Mac, or Linux, should be plenty easy. And you need to set up an editor. The Haskell.org site recommends using Visual Studio Code. I think that is a fine recommendation. Because I'm a weenie, I'm going to be using Emacs to do it, and of course running things either in the terminal or in a shell window in Emacs. I've actually noticed when doing this inside of Emacs, there's some weird echoing artifacts, so I may just use a terminal for it. However, for our first few weeks, we're actually not going to be doing a lot in our editor. Instead, we're going to be using code.world. This is an online editor and environment for Haskell and for an API, a kind of toolkit for our framework for Haskell called code.world. To access it, just go to the URL code.world. The reason we're using code.world, or one reason we're using code.world is the environment provided by or used by Joachim Breitner's fall 2016 CIS 194 class from the University of Pennsylvania. So we're going to be using that in future episodes. And then at a certain point, we're going to transition from code.world. Code.world is really interesting. I do suggest the first thing you do after going to that URL is create an account. And that's so that it will actually save your work, because it would be frustrating to spend a week doing some work and then suddenly lose it. Once you have the account created, your files will show up right here in this sidebar. So if you can see, we are actually running a program here. We have a very simple program here in Haskell. I'm not going to explain all of this at the present time, and you can run your program. It compiles it and it runs it. If you want an alternative to the things I've suggested, have at it. I don't control you. I'm not the boss of you. You can program on Replit if you want a different website to use Haskell on. I've done that in the past and it's worked pretty great as well. Now, despite me saying that we're not really going to get into it today, I can't leave you with no programming whatsoever. So I've made my terminal window nice and big. I've given it a ludicrously large font. And let's take a look, once you have Haskell installed on your system, how we can do some interactive typing at it. And we're going to look at a few expressions. So what we're going to do here is we're going to run GHCI. GHC, Glasgow Haskell Compiler, is the compiler. GHCI is interactive. So right now, we're not actually using any kind of program or, we haven't written any Haskell code at this point. We're just going straight into GHCI. Well, let's type a number. Let's see what happens. All right. So I immediately get back 1, 2, 3, 4. What's that? Well, that's a number. If you started GHCI without doing any kind of setup, you probably also got a very nasty looking warning about how GHCI needs to infer the type of this number because it's not quite sure what it is. This is one of the drawbacks of Haskell, in my opinion, is that it's super verbose. It would rather be explicit about all the things that might go wrong than just letting you get on with it. It's kind of like having a very nervous lawyer watching everything you do. I actually went, and I'll show you, I went and set that value, F no warn type defaults, because it was killing me. I think we could even do this inside GHCI. We could say warn type defaults. And now if I type 1, 2, 3, 4, we get that error. And then at the end here, it actually does go ahead and emit that value for us. But this is going to be a really frustrating YouTube video if I leave those warnings on. So I'm going to turn them back off. So how do we know what that is? Well, one of the nice things about GHCI is you can inquire about the type of pretty much anything you're typing. We could say : type, this is kind of a meta command, 1, 2, 3, 4, and it tells us something about 1, 2, 3, 4. Now, how to read this type we're going to get into, because this actually isn't just a type, this is actually a generic type decorated with a type class. But if I fall down that rabbit hole, we'll be here forever. We can type characters. That's a single quote. That's the letter O there. Poor choice. Tells us it's type char. We can type a string. What type is that? Tells us it's a string. Now the Haskell string type is famously bad, and there are a large number of alternatives to it. The one that I'm most familiar with is in a library called data.txt. And when we do our code world work, you're going to see that most of the code world APIs that want textual data are going to be taking text rather than a string. And we'll talk a little bit about how to convert back and forth between strings and text there. We could type a decimal. And again, we're going to see, somewhat surprisingly, a generic type value decorated with this type class called fractional. There are some other basic types. So there, I typed something with no quotes, no single quotes. I just typed the word true, and it spat it back at me. That's because the word, I shouldn't say the word, the token true is of type bool. So what is type bool? Well, here's another meta command. We can type in GHCI, we can type info and give it a type. The most important line for you right now is that very first line. Data bool is false or true. And it also tells you where it's defined. And all of this stuff here is telling you essentially what type classes it implements. We can, for example, this says that it implements the EQ or equality type class, which lets us do this. Nice to be able to do that. So now I've typed something that is more than a single glyph. So what does that mean? Well, let's use type to inquire about it. Okay. It immediately evaluates that whole expression and gives us the type of it, which in this case is just a Boolean. So Haskell is all about functions, and we do call it functional programming. Part of the gymnastics I'm doing here and why I'm using GHCI rather than writing code is I'm trying to see how far can we get before we introduce something that looks like a function. I want to really linger here at the expression level because evaluating expressions is 99% of what you're going to be doing when you're writing functional code. What expressions can we do? Well, so I typed a glyph here, true, a token here, true, with no quotes. What happens if we type nonsense? Okay, here we get an error. So if you type this in Python, what would you see? Let's find out. Okay, Python tells you nonsense is not defined, but GHCI is telling us, I can't remember what it said, data constructor not in scope. So what does that mean? Well, it means because we started nonsense with a capital letter, thank you, Haskell, it thinks that that is not just a symbol, but it must be a data constructor for some type. So the gotcha here that I'm pointing out is that tokens that start with capital letters have a special privilege in Haskell, which is that they're treated as data constructors. Well, what happens if we type nonsense in lowercase? Okay, again, we get a very specific error message. We don't just get nonsense not defined, we get variable not in scope. And this word variable, you know, it has a term of art in Haskell. This is variable in the sort of mathematical sense. So that variable nonsense could be bound to a function. Okay, let's clear the screen and get these error messages off. What else can we do? Well, I did use the word bind. Can I bind a name to something that without using a function? And Haskell provides a mechanism, actually provides several mechanisms to do this. So we remember we don't have that variable. We could use what's called let syntax to bind this name. Let nonsense equal 55. Tells us it's a number. There we go. It even tells us where we defined it. So what we've done there is we've now bound a name. Now, arguably, by doing that, I've just defined a function. It's a very simple function. It only has one value, 55, always. It's essentially a constant function. But we could also define that value in a certain scope by using let in. So let's say let So what just happened there? It looked like nothing happened. We said let myval equal 55 in myval. Well, Haskell did two things. First, it bound the number 55 to myval, and then it evaluated the whole expression. And the whole expression was just this very boring thing, myval. But then once that expression has been evaluated, it goes out of scope. I can't use that anymore. We could use more complicated expressions. And we get a value back. But again, now it's out of scope. Other basic expressions, the one you certainly expect is a conditional. Syntax is if, then else. What happens if I do this and leave off the else? Can't do it. It's an expression and all parts of that expression must be defined. So if you've done any programming at all, so far, everything I've shown you seems pretty straightforward, right? There's one other wrinkle to this, which is that expressions have to evaluate to a static type, which means that I can't do this. If true, then hello, else 5, right? So if it's true, I want a string, and if it's false, I want a number. And so here it's complaining that 5 does not yield a string. That's this no instance for num string arising from the literal 5. We're rapidly approaching the point where we're going to have to talk about functions, but I want to give you 2 more types before we do that, because we're going to be making pretty heavy use of them. So first I want to talk about sum types. These are very similar to what you probably called an enum in some other language. So let's say I wanted a type that represents the day of the week. We're going to use the data directive in order to introduce a new type. And we'll just call it day of week with a capital letter. And then we're going to give it a bunch of constructors. Pretend I could spell. Thursday, Friday, Saturday, and Sunday. So now we have this type defined, and let's switch over to our REPL. And in order to do that, I'm using Cabal instead of Stack. That's one of 2 build systems that Haskell has. I think there's actually more, and we can see immediately I have a typo, the compiler tells me, which is great. And you can see I have that leading pipe, just a normal typo. A quick word about mistakes. I'm going to make a lot of mistakes. The ones that interrupt the flow of the video, I might edit out just so that it's bearable to watch. But when possible, as in this case, and I think that there's learning value in the mistake, I'm going to leave it in. Making mistakes is part of programming. Making mistakes is how we learn in engineering. And so by that standard, I must be a really great learner because I make a ton of mistakes. All right, so now we have our sum type. Let's flip over to GHC and reload. Now we should be able to introspect that type, right? We could see it's defined here. And we could see we have these constructors, Monday, Tuesday, Wednesday, etc. Now, these are the inhabitants of the type. These are the values of the type. So if I look at, say, Thursday, Thursday isn't a string that represents Thursday. I mean, it is in some sense, but Thursday is the actual value of that type. The day of week type can have 1 of 7 values. Thursday is one of those values. So logically, if that's a type, or excuse me, if that's a constructor, what would happen if I were to type a constructor in at our REPL prompt? Well, it should print it out, right? Well, maybe not. Let's see what happens if we try it. Okay, we get another famous Haskell error message. No instance for show day of week arising from a use of print. The REPL was trying to print it. So this is where we start. We're just going to barely glance at type classes. There's going to be a lot of discussion in type classes in future videos. This is where I just want to give you the barest introduction to it. So a type class is similar to a protocol or interface in other languages such as Java or Objective-C. I'm sure that Haskell purists are jumping up and down right now telling me that type classes are much more powerful than that, but that's the basic idea. So what this is saying is print the command that the REPL was trying to use, or the function that the REPL was trying to use, wants whatever type it's trying to access to implement this show type class. And if we flip back to our Emacs window, there's really nothing here. So there are 2 ways essentially to implement a type class. We can implement whatever function that type class requires and declare that we're implementing it, or we can just do what's called deriving the type class. There are default implementations for certain type classes, and show is one of them. So let's go ahead. I don't know if it's going to work if I indent that way. Let's find out. So I'm just going to put deriving show to get the default implementation. Was that going to work? Let's find out. It looks like it works. So now if I type Thursday, it just echoes the string Thursday, which happens to be the same string as that constructor. All right, so that is sum types. Product type is a tuple, so it's several values bundled together. So let's say we do Tuesday 5, and let's give it a name. Right. Go back over to our terminal, reload, and we don't like it. A top-level binding with no type signature. This is a case where we're being told that we don't have a type signature for this. However, I don't want to use type signatures just yet because I'm going to talk about them in 3 minutes. So I'm going to turn off that warning. Haskell's trying to do me a favor here by helping me recognize where I'm using poor style, but I know I'm using poor style here. All right, let's try that again. Okay, it's loaded. We can type tuple, and we get this tuple, Tuesday, 5. So what's the type of this tuple? Well, let's look at it. It's day of week, comma, integer. I think the comma is technically the constructor for the tuple, not the parentheses, although very often we use the parentheses anyway. What happens if we do this? I think you can extend this out as far as you want. Right. So we have tuples. These are generally called product types, and both product and sum types are considered part of a concept called algebraic data types. And one of the I think one of the best things about Haskell is its really excellent support for algebraic data types. They help you reason about problems very effectively. All right, so now let's talk about type annotations. And in fact, let me move my comment up above that. So tuple is a variable. Tuple is arguably also a function that takes no arguments and returns one argument. So best practice when you're defining a function is to annotate the function with the expected type. And we do that with the double colon operator. Okay. And so I think this is of type day of week. And I'm going to declare that is actually an int. Right. Let's save it. And let's see let's turn warnings back on. And make sure we don't get that warning. Great. Now, let's look at that type again. Great. Now you could see there's a difference here. When I declared that type annotation, I declared it as day of week int. When I introspect the type here, it is indeed day of week int. When I didn't provide the type signature, it was different. It was integer instead of int. And so what happened here is Haskell tried to infer what type I probably wanted. And there are rules and best practices as to how that happens. The fact that type inference happens is a great convenience because it means that you don't always have to declare these types, but if you want a specific type, it's usually considered a good idea to actually include an annotation. And we're going to try and use annotations for everything we do. We can change this to a float. And what will happen here, because normally the float syntax would look like that. Let's see if it'll correctly infer that that 5 is a float. I think it will. Okay. Right, and you could see here that when it went to print that value, it printed it as if it was a float, even though we typed it as something that looks like an int. So type inference is doing a lot of heavy lifting for us here. What happens if we intentionally have an error here? And you've already seen some error messages that look like this. But let's say that this is day of week and a string, and we're creating a tuple that has a day of week and a number. Save. Right. as expected, we get an error. And what it's telling us here is that essentially it's a very long-winded way of saying 5 is not a string. All right, at long last, let's start talking about functions that take arguments. And to make this a little easier on myself, rather than using integers, I'm going to create a new type . Let's do that. Let's create a new type called activity, and our activities are work and play. And I'm going to move this, out of our way, just so that we can actually do our work down here. Let's make a new function called schedule, and let's spell it right. How about that? So what is this function going to take, and what is it going to return? Well, I want it to take a day of the week, and I want it to return an activity. And we've got this arrow here, which is a dash and a greater than sign. And if you've seen me doing any of these program videos before, you may have noticed that I'm very, very fond of a certain font that kind of creates ligatures of these things and turns them into what looks like actual arrows. I turned them off for this video because I didn't want people sitting at their keyboard saying, well, how do I type a right arrow? How do I type something that looks like this cool ligature? Later on in the video series, maybe I'll turn those back on if I feel we've reached a certain level of agility with them. All right, so this is the type that I'm declaring. I'm going to be faced with the question of how abstract to get here. And I promised you in the introduction that I was going to try to stay as concrete as possible. So what I'm going to do here is I'm going to start a little bit abstract, and then I'm going to back out and get more concrete. But I have to introduce the abstraction in order to motivate the concrete version. So we've got this function schedule, and let's give it a variable here on the left-hand side of an equals sign. Okay, so we have a variable called day, and let's use a conditional here so that I can keep this abstract thing in one line. So let's say if day is equal to Monday, then work, else play. We have a very light schedule. I'm envious of this person. So a thing I like to do when I'm learning a new language is type something and then ask myself, is it going to work? When I go over to the compiler or to the REPL in this case, is it going to work? I'm going to tell you that I don't think this is going to work, and I think the reason it's not going to work is that I have not yet taught Haskell how to compare days of the week. Let's see if that happens. Go over to our terminal. We get this very long error message, and what it's complaining about here is that there is a type class called EQ, which compares whether two things are equal, and I have not implemented it. And again, for the second time, I'm going to just derive that type class because simple equality is actually derivable. Now that I have two of these things, I need parentheses around them. So, and let's go ahead because I know we're going to need to do it later. Generally a good idea to just go ahead and derive those for your simplest type classes. All right, we've saved that. Okay, so now we have this schedule function. We can introspect its type, takes a day of a week, returns an activity. Oh, in my terminal, I'm using my, my fancy font, so you'll get to see it there. So let's say our day of the week is Tuesday. We expect this to return play, and I think this will work. Great. Great. We really want to test all of the values in order to be sure that it works, but I think this is enough for now. All right, so I said that I wanted to get less abstract here. Let's do that. So what did we do in this function? Well, we bound this term day, this word day, this variable day, to whatever was going to be typed in this case, in the REPL, whatever was going to be passed into the function. And then we did this conditional. But we don't have to be abstract at all. We don't have to bind any names at all if we don't need them, right? Suppose I don't work for a living. Would be nice, wouldn't it? I could use this underscore, and this underscore is Haskell syntax. That means it's some argument. I don't know what the argument is. I'm not giving it a name, and I'm never going to use it. And so if I don't work for a living, then I play all the time. Maybe I make YouTube videos about Haskell. Let's reload it. And now we have not changed the type. This is still takes a day of the week and returns an activity. Oh yeah, that's the stuff. I love it. That's a goal right there. So that's one way to be not abstract, is to just say it doesn't matter what it is, right? But we can be more concrete than that. Maybe we have a finite or a very small number of choices, options. Here we have 7 of them, right? So we could say, well, I'm working on Monday. We could literally type in all of the things that we care about. We can go out of order. We're not obligated to go in order. All right, so now I've said that we're working on Monday, Tuesday, and Wednesday, and we're playing on Sunday and Saturday. So again, will this work? What do you think? Let's try it. It kind of worked, and it kind of didn't. We got a very dire warning that tells us, and this is, I complain a lot about Haskell error messages. I'm sorry, it's not going to change. I'm going to keep complaining. This one's pretty good. This tells us that the pattern matches are non-exhaustive. So what does it mean, pattern matches? Well, what we're doing here is a pattern. This is called pattern matching. And so we're saying that if this argument is Tuesday, we're going to do this, and we didn't provide all of them. And in fact, this error message even tells me what patterns were not matched. But it did compile, right? We got this OK1 module loaded. And if we provide one of the constructors that we did define something for, we get an answer. What happens if we provide a constructor for which we did not provide a pattern? We actually get a runtime exception. Generally, hopefully pretty rare in your code. The warnings will help you know when this is likely to happen, but you can force it as we did here. So we could fix this by going in and adding elements for Thursday and Friday, but let's do it a different way. Let's use what we just learned about I don't care what this is, and say for any day that I haven't defined, for any pattern that doesn't match, it's a work day. Flip back here, and now we're back in the chain gang. And in fact, obviously in this case, if I really wanted this to be the way I was going to implement the schedule function, I would probably do it like that. Now, real talk, along with algebraic data types, pattern matching in function definitions is one of my favorite things about Haskell, and we're going to be doing a lot of it. The syntax is very powerful, and it does more than you think it can do. You can basically pattern match on anything that has to do with the structure of a type. Now, we haven't seen any kind of complicated structured types yet, so it's hard to explain this. So rather than get too abstract about it, we'll save that for when we do start using structured types. A question that might occur to you looking at this is, well, seems wasteful to have 2 lines for Saturday and Sunday. Can we do that in 1 line? And I'll jump straight to the answer. Not really with pattern matching, but there are other structures with which we can do it. But let's try it. Let's see what happens. It's not going to work. This one I'll just tell you point blank. Like, could we do something like this? Comment that out. Gosh, maybe I need that. Will that work? And the answer is going to be no, because that's not what pattern matching is kind of working at the type level, and that ain't a type. That's really an expression. So how could we do something similar to that? We would do this with a concept known as a guard. Let's make a new version of our schedule function. We'll call it schedule 2. The Haskell weenie, I'm making a new variant of this function, is to do that. So we'd make schedule like that, and we'd do schedule like that as our second variation. I think this is math cosplay. I'm just calling it schedule 2. And it's going to have the same type signature. So what if we wanted to have that Saturday and Sunday on the same line, otherwise return work? Well, obviously we could use an if-then. That would be fine. But there's another structure we could use, and it's called a guard. So we're going to reintroduce a name for our function parameter. We'll use day. Go to the next line, indent it, and say if the day is Saturday or the day is Sunday equals, now we're defining the function, play. Otherwise, that is a keyword. Otherwise, here is a keyword, work. And we have now defined this function. Let's see if it works. This one I think should work. If it doesn't work, I've made a mistake. Great. Typo. Told you I'd make mistakes. Great. So now it's work for every day except Saturday and Sunday. I actually put it on screen and then I removed it. Let's go ahead and define that yet another variant of schedule. We'll also define it with the same type signature. And let's put our first abstract version back. Indentation seems funny here. Haskell can be very persnickety about indentation, and I gotta tell you, I've been using it for a while, and I'm still not fully comfortable with when it demands perfect fidelity and when I can put it wherever I want. That's how I want this to look. Let's see if it takes it. Great. And I'm not going to bother to type it in here. Merely reloading the REPL and having it tell me there's no errors gives me the confidence that this is implemented correctly. So this is going to be a theme. Theme is, as you use Haskell, there's more than one way to do it. And usually there's a lot more than one way to do it. I am positive that I have not exhausted the number of different ways to write this function. And something that you're going to have to choose for yourself is, what are the idioms that you are most comfortable with? I can tell you that I personally find myself gravitating to patterns whenever possible. I just find them beautiful and elegant, and sometimes they're inconvenient and you can't use them, but whenever I can use a pattern, I try and use it. All right, one more concept that I'm going to introduce here, and I'm not going to go deep into it because it is on the abstract side of the fence, and we don't have a task yet that motivates or necessitates the use of it. But we will pretty soon, and when we need it, we'll use it. But I want to just introduce the jargon, which is that type arguments in Haskell can be what's called, $10 word here, polymorphic. So all of our type annotations here have been very specific. Take this type, return this type. But we can use, instead of using a type in our type annotation, we can use a lowercase letter, a variable. So typically the best practice that people use that you're going to see out in the wild is people give these generic types name like A and A, just to be a jerk. I'm going to call this some type. In fact, let's be even more dramatic and say unknown type, unknown type. Right. And that is not a type annotation. That's a type annotation. So now we have a type annotation. So if we go back to our REPL or to our compiler and try and load this, we're going to get an error because we have a type annotation and we have not actually bound that type annotation to anything. There's no function here. So how can we define a function? Well, I don't actually know what this function, what I want it to do yet, right? So we can define a function here, and there's a couple of ways to do it. Actually, for this particular function, I'm lying. There aren't a couple ways to do it. There's only one way to do it. But there is some syntax here that I wanted to introduce. So one thing I introduced earlier was right over here, this use of the underscore on the left-hand side of the equal side to mean doesn't matter, I don't care, whatever. We could use that underscore on the right-hand side. Now, here it has a slightly different meaning. Here it just means I don't know. What does the compiler do if you tell it the implementation of something is I don't know? Well, Haskell, there's more than one way to do it, provides two different ways, at least two different ways to tell the compiler I don't know. So let's see what happens if we reload with this underscore on the right. Whoa, we got a lot here. I'm using my huge font so it even goes past a screen. So that is the most important thing. Found whole. The underscore on the right-hand side of the equal sign is a whole. And the main use for the whole is to get an error message from the compiler. You're telling the compiler, you tell me what you think should go here from a type perspective. Now, because this is a maximally generic type variable, the compiler actually doesn't know what should go there. And it just says it's a rigid type variable, so it has to be some type. But it's bound by this type for all unknown type. It could be anything. So in this case, the whole is not that useful to us. That error message is pretty daunting. And that's because this is a maximally generic type and there's really no useful information. If you're working with slightly more concrete types, types of a specific class, or a type that is a really concrete type, and you have variables that are of that type, the compiler will suggest, did you mean to use this one? Did you mean to use this one? In fact, if you're using an IDE, that IDE may be able to autofill holes for you in certain cases. But let's look at another way to tell the compiler that you don't know what goes somewhere, and that is with the keyword undefined. Now, if we reload it, we can actually run our code. We cannot run that function. If we try to actually run that function, we will get this error saying that we haven't actually applied an argument to it. Let's say we do that. We're going to hit an exception because we don't know what is actually, what to do if someone passes, in this case, 777 into this function. So I'm going to leave you with a challenge and a homework. the challenge is, and this is the sort of thing where if you know, don't spend a lot of time on it. If you don't know what this sum function does, I'm telling you that because we have no type information here, it's a completely generic type, there is only one function in the entire universe that is a valid implementation of this sum function. So your homework, your challenge is figure out what that function is. For bonus points, tell me what it's called. If you already know, there's no bonus points if you were taught this in a class. You don't need to leave this in the comments. I would, in fact, ask that you don't. Just for your own education, learn what is this function. So what is the homework? The homework is to get ready for our first lab video. So as I said, I'm going to do kind of lecture-like videos like the one you're watching now, and then I'm going to do lab videos where I work through some exercises from different online courses. The particular course we're looking at today is Joachim Breitner's CIS 194 from the fall of 2016. The URL will be on the screen right here. It will also be in the notes for this video. What you should do is read the lecture notes for week 1. That's Haskell Basics, Functions, and Pictures. And this is where we get to play with pictures rather than abstract mathematics. And then my suggestion is you should do homework 1. Homework 1 is fairly straightforward. It's really describes what you need to do in adequate detail. You can ignore anything about Piazza. That's stuff for the University of Pennsylvania. And most importantly, he provides a starting point in Code World, and that's where you should do your work. If you really want to do it in your own IDE, you can try, but there's some aspects to that make it a little clumsier. I will be doing the lab video in Code World. If you don't want to do it yourself, you can, of course, just wait for the lab video and watch it. I think you're going to get way more out of it if you do it yourself. Now, when you launch the homework assignment, you're immediately going to be confronted with an error, and that's because this was made in the fall of 2016, and the Code World API has changed in the intervening, 8 years. So here's how to fix that. If you want to learn how to fish, the way I did this was I searched for this term, path, in a Code World context on the Haskell API site, Google, and discovered that it was deprecated. So take this word path and replace it with the word polyline, P-O-L-Y-L-I-N-E, and at this point, the code will run. Now, the way you actually do this homework assignment, this is all explained in the written materials, but you can see all of these exercises, all of these functions are undefined. You're going to replace that undefined with your own code. Now, one more thing, when you are doing your homework, you probably want to save your work. So after launching Code World, make sure you click this sign in button and actually create an account if you need to and sign in so that you don't lose your work next week, because we're going to be building on the things we do this week in future weeks. All right, the channel is Tea Leaves Programming. The series is Programming Like It's 1979. I really appreciate your coming on this journey with me. Don't forget to like and subscribe, and if you want to support what we do here, become a channel member. Thanks so much for watching.